Good morning. How are you? I hope you had a great night. So today we will continue with the review lectures. In this case, this will be a review lecture. This is the second review lecture. Okay. Before starting, I would like to show you that I have added on Canvas. Let me check if I can show you this. So I have added here a new module for this, the remainder of this week and week 12, in which I have included, apart from the slides and the review lectures that we are going to, that we did yesterday and the one we are doing today, I have also placed here some videos for you, just in case in the next week, in week 12, you would like to see summary videos. So here are 3 summary videos summarizing each of the 3 parts that we have covered in the module. Okay, so those are published there for you. Okay, so yesterday we covered procedure calls. Today the next most voted elements were compilation and execution flow. Let me show you. I think I have here the votes. So the next most voted elements, apart from procedure calls that we covered yesterday, were compilation and execution flow. And then addressing modes and binary division has the same votes, but as we have several videos from binary division and we don't have, and we only have the lecture for addressing modes, I have preferred to explain again addressing modes, because as mentioned, we have very many different videos explaining binary division. For lab 3 and so on, we have additional videos. Okay, so this is what we are going to see today then. Okay, so let's start then with the compilation and execution flow. Someone is asking if this is the last lecture. So yes, this is the last lecture. Weeks 12 and 13 are assessment weeks. Okay, so in the case of this module, the assessment is in week 13. You already know that, but yes, this is the last lecture. But as always, remember that you can still use the ticket system or email us if you need further assistance before the exam. And remember that this afternoon we have the last lab session, and as always, at 1 we will publish the lab, and then on Friday at 1 we will publish the results. Okay, then, so let's start with the compilation and execution flow. Now that you have an overview of what an overview of the whole module, maybe you understand this better. So what we have in the beginning is a high-level language program. It could be in any programming language, programming language that you use. It could be, in this case, I'm showing an example from C, but as I have mentioned different times, it could be Java or any other high-level language program. So what happens first? This program is compiled. What means this? That the initial high-level program is converted into assembly language program. Remember, what we have actually seen in this module has been assembly language program. So we have been working mainly in this area here. Okay, we have assumed that this has already been created, and we have assumed that we were here. We have also at some points we have just been implementing programs directly in assembly language, just for showing you how this assembly language works. But usually what we do is we use a high-level language, and the translation to an assembly language is done automatically. So this will be the step 1. Okay, the program is compiled. So we have, from a high-level programming language, we obtain an assembly language, which is just, for instance, here we are showing the equivalent of the of this C program in RB8. Remember that what we have seen in this module was something similar to RB8, which is called LEGB8, is a reduced version of RB8 just for teaching. Okay. So what will be the next step? So we have our program compile, and we have it in assembly language. We have assembly instructions. So then the next step is called assembly. The code, these instructions in assembly programming language are converted into binary programming language. And you also have seen now how to do that. So you actually, what we have seen in this module is how to do this process manually. But the good news is that this is done automatically. Okay, so why have we seen in this module how this is done manually? Because we want you to know how internally a computer works, just in case in the future or at some point you need to have this knowledge. Okay, so this process will happen automatically, but here in this module we have learned actually how to do this, how to implement a program in assembly language, and how to convert those instructions into binary matching language. Okay, so those two steps are very clear. So then the third step. Is what we call link. Let's say that apart from my program, I'm using programs that I have used previously or existing libraries or things like that. So in this case, there is a tool which is called linker that just links my program with other libraries, external libraries and modules that I am using. Okay, and then the fourth step is actually loading the program into memory. And you have seen how to do this in the labs. Okay, so what this means? This means that I have from the previous steps, I have the binary matching code. Okay, so what I'm doing in this step, in step 4, is just loading this program into memory. And you know how this memory looks like and how the program is loaded. So in this case, each of these lines are 32 bits, and each of these lines refers to an instruction. And what happens here, what is in the end? So once we have the program loaded into memory, we are ready to execute this program. So instructions will be executed one by one. Okay, so what will happen here? The control unit will fetch an instruction and it will tell the data path, okay, perform this operation. For instance, imagine the instruction in red is an add operation. So what will happen here? The control unit will fetch this instruction and it will say, it will decode it, and it will say, okay, this is an add instruction. So then I will place the register 0 here, the 10 here, and I will tell the arithmetic logic unit to perform an ALU. Why? Because in this case, if we go back to the initial example, we see here that this instruction is adding register 0 to register 10. Okay, so this instruction here, when it is actually executed, is fetched by the control unit, and registers are accordingly selected, and the operation in the ALU is already selected. And you know how this is done. So you know that for selecting the add operation, we have here a multiplexer in which we select that we want to do an add, and we know that in register files we have also a decoder for selecting the file in the register file, for selecting the register in the register file that we want to select. So you actually right now have an overall view of all the process. So you know what happens since I write my program until it's actually executed, and you even know what it looks like this hardware inside the ALU or the register. You have the basics of logic design also. Okay. So now I have an exercise for you. I'm going to, as usual, I'm going to copy a link to a form is in the Q&A, and I'm going to give you a couple of minutes. Okay, the question is just having these steps in the compilation and execution flow. You need to select the correct order in which these steps happen. Okay. Okay, so the time is over. Let's check the results. So here, okay, most of you get the correct answers, but there are some people who already have some confusion. Okay, so let's check what are the correct answers then. Okay, so what happens first? As we have mentioned, the first step is compiling. So the compiling the program. So the program is compiled into assembly language program. So here, for instance, we have a C program and it is compiled into assembly language program. Okay, in assembly instructions. Then this assembly language program is assembled and is converted into matching language, zeros and ones. Okay, so high level programming language, assembly language, and matching language. And in this at this point, there is something called linker that apart from using or the module generated by from our program, it's also linking it with existing modules or libraries that I'm using. For instance, imagine that in my program I am printing something in the screen. I don't need to implement the routine which prints displays things in the screen. This is already done, so I just use a library which do this operation. So the linker will link to that to that library in my code. Then we will this linker will generate the real executable with my code and all the linked modules and libraries. And once we want to actually execute this code, we load the code in memory. We have just seen how this is done and in what this consists of. Okay. Okay then. So here we have what we have just explained, but just for you in the slide, just in case when you study you prefer to read the slides. So this is just what we have mentioned. Okay. Okay then. So what happens? So there are some compilers, some tools that, in order to make this process faster, combines some steps. For instance, some tools produce directly object modules and from the high-level programming language. So the intermediate assembly step is just combining the compilation process. And there are others that use something called linking loaders that performs the linking and the load step together. So graphically, this will be that those steps, the compilation and the assembly, are performed together by some tools, some compilers, and there are also others that perform the last two steps together. We will see what static linking means in a while. Okay. Yeah. Someone is asking if the slides are not on Canvas yet, but they will be. Okay, I will upload them. Yeah, they are not yet on Canvas. Sorry for that. Okay, so then if we are using a Unix operating system, the files, there is a convention for the suffix of each of these files. For instance, if my program is a C program, the file will have the suffix C. So it will be my program .c, or the name I want to give to my program .c. Then for assembly language, we will have the suffix S. For object files, we have the suffix O, and as I mentioned, we are going to see in a while what means static library and dynamic library, but in the case of static libraries, the suffix is A, and in the case of dynamic libraries, the suffix is SO. And if by default executable files are called A.O, but usually what we do is we rename those. We just give the name of the original file. So in this case, usually the executable is just called X without any extension. This is in Unix, remember, in Linux, not in Windows. In Windows, it's a bit different. Okay. So then what we have seen regarding the compilation and execution flow is that for producing an object module, the first thing is that the assembler or the compiler translates the program into matching instructions. Then the linker just combines all the modules and produce all the modules and external libraries and produces an executable image. And then the program is loaded into memory and executed. So what does means loading the program into memory? So we have seen in a slide before that we have just placed all the zeros and ones there in memory. But what actually happens, and now this makes more sense because we have seen all the module. So what actually happens is that the instructions are copied to the text segment of the memory, and this data, the registers and so on, are initialized accordingly. And also, if something is in the stack, we set up also the arguments for this for the program on the stack, and this includes initializing the registers, the stack pointer, and the frame pointer, and so on. Okay. And then we just start in the main routing. So this is what we have seen in previous lectures. So the program is loaded here in the text segment, and in case I have I'm using the stack, the dynamic data will be here. So this is what is doing this step, loading the program in memory. This is what is actually happened, and we have seen this in labs and in lectures. So this should be clear now, okay? Someone is asking if we need to know the suffix endings for the exam. No, they are just as an example. And remember, the exam is open book. So if I ask you the suffix, you just need to go to the slide. So no, you don't need to know that. You need, in case you need to use this in the future, you need to know. Okay, I remember that this file has a suffix, and you just look for it, but you don't need to know it by head. Okay. Okay, so then let's see what is static linking. We have seen that when we link a program, it consists on, I have my initial program, and if I'm using external modules or external libraries, I need this linking stage is going to put all this code together. So the static linking means that all the program is combined together and is static. It will not change. So it will be like a big program, okay? Combining all the modules and external libraries. So what happens here? What happens here is that all the code will be, as I have mentioned, in my executable, okay? All my initial code and all the external libraries I am using and everything. On the contrary, with dynamic linking, what happens is that I don't add the external modules and the external libraries to my program. I just add a link to them. And when I actually call in them at execution time, then those external libraries will be actually called. Okay, this is called dynamic linking libraries. In Unix, we have seen the extension is SO. In Windows is DLL. Okay, and as I have mentioned, these dynamic libraries, dynamic linked libraries, are only called when they are actually called in execution. Okay. So they are not part of the executable. My executable just contains a link which will be executed at runtime, at execution time. The advantage of this is that if I update the library and I am using dynamic linking, I will pick the new library version without modifying my executable. On the contrary, if I am using a static linking, I will need to recompile my program in order to recompile and do the linking stage again in order to put the new version of the library in my executable. Okay, as you can guess, an executable generated using dynamic linking will be smaller than one with static linking, okay? Because the static linking contains all the libraries, but the dynamic linking just contains links. Okay, so this is for programming languages like C. But what happens with Java? So with Java, a program is first compiled into a binary version of something called Java byte codes, okay? And this contains all the addresses defined by the compiler. So at this point, the Java program is ready to run in the interpreter. This interpreter is called Java Virtual Machine. You have probably heard this concept. And what this Java Virtual Machine is doing is just linking to the desired methods in the Java library while the program is running. At some point, to achieve better performance, the Java virtual machine can call something called the just-in-time compiler, okay, which can select methods into the native machine language of the machine on which it is running in order to make to increase the performance. Okay, so this program will be portable, can run in any machine, but if I'm running in a specific machine and the just-in-time compiler can compile the program for that specific machine in order to increase the performance. Okay. Okay, so this is what I have already mentioned in the previous slide. It's just here for you as before, if you want to study from the slides, just to have it here also written. Okay, so with this, we are done with the compilation and execution flow. I don't see any other question. Okay. So just let's move on to addressing modes. Okay, the idea of addressing modes is that imagine that we cannot indicate in the 32 bits which has an instruction, we cannot represent the data we want to give to a variable or a register. Imagine that we want to initialize a register all the 64 bits of a register. So if the register has 64 bits and we have instructions of 32 bits, we are not able to initialize all the bits in the register. Okay, so in that case, we need something additional in order to be able to modify completely a register. So let me show you an example. So imagine, for instance, with the add I instruction. Okay, here I can initialize register 9 to 1, to 2, or whatever, but I'm limited to 12 bits. So if the number I want to put here is larger than 12 bits, then I cannot use this operation to initialize register 9. So yeah, what should I do then? For these things are intended the addressing modes, what we call addressing modes. First, we have something which is called wide immediate operands, and then we have also the addressing modes by itself. Okay, so let's see first the wide immediate operands, which are those two instructions in LegVH, mov set or mov zeros and mov K, which the K stands for keep. So let's see how these instructions work. So these instructions set a register in sets of 16 bits. So if the register is 64 bits and I cannot modify in one instruction all the 64 bits, so then what I will do is we modify first 16 bits, then the other 16 bits, and then the other 16 bits, and then the remaining 16 bits. It's like dividing the 64 bits in 4 parts, and in each instruction I modify one of these 4 parts. Okay. We are going to see how these instructions an example later, but what we actually do is we use the logical shift left in order to indicate if we want to update the first quadrant of the register, the second quadrant of the register, the third quadrant of the register, or the fourth and last quadrant of the register. Okay, the difference between mov set and mov k is that with mov set we modify the quadrant, the first, the second, the third, or the last one, but in addition we set the rest of the bits in the register to 0, and with mov k we modify the one of the quadrant, but we the rest of the bits remain unchanged. Okay, let's see how those instructions are actually defined in LegVI. So they have what we call IWU format, which is wide immediate format. And as you can see in the screen, we have an operation code of 11 bits, we have an immediate value of 16 bits, and the register we want to modify in 5 bits. So here you can see that before with the add I we only had 12 bits, but now here we have 16 bits, and here we put the register. So with this operation then we can modify this register 16 bits of the register. And as I have mentioned, as the register has 64 bits, so we can indicate which quadrant of the register we are modifying at in each instruction. Okay, so we have also the immediate format, which is a variant of this wide immediate format in which the operation code has 9 bits, and there is a second operation code of 2 bits that we are going to see now how is intended for how do we use this operation too. So what we have seen till now is that, okay, we have the operation movset or movk, we have the register we want to modify, we have the immediate value 16 bits, and then for indicating the quadrant we just put the logical shift left instruction, and then we indicate the quadrant. This quadrant can be 0, 16, 32, or 48. Okay, and now, for instance, for movset, the 9 bits of the opcode are those ones. For movk, the 9 bits of the opcode are those ones. And depending on op2, we will modify one quadrant or another. So in the case of this quadrant is 0, op2 will be 0, 0. In the case that quadrant is 16, op2 will be 0, 1, and so on. Okay, everything is clear? Okay then, so let's see an example. For instance, if we have this instruction movset register 9 153 and logical shift left 16. What this means? So this means that with the set we are going to set to 0 all the bits in the register, and we are only to modify the quadrant indicated here. So we are going to put this number into the quadrant we have selected. In this case is the second quadrant, and as we have a set here, the rest of the bits are going to be 0. Okay. Then what we are going to see is another example, in this case with the k. Okay. In this case, I will modify the same quadrant, but the rest of the bits will remain unchanged. Okay, so what will happen here is the only quadrant changing is that one. And as I have here the k, I keep the rest of the bits. Okay, makes sense? So imagine that I'm going to execute now this code here. The content of register 9 after executing this instruction will be that all the bits are set to 0 because I'm using the movset, and I'm modifying the first quadrant. So in the first quadrant, I'm adding the number 255 in decimal, which is the number in hexadecimal. Similarly, if I want to modify the third quadrant, so I will do this. In this case, I'm also using the movset, So all the bits will be set to 0, and I will put the number 1 in this register. Okay? Now I have an exercise for you. I'm going to copy again a link for a form in the Q&A. Okay, and what I want you to do is imagine that we are going to execute those instructions, and I want you to answer what is the contents of the register 9 after executing these instructions. The answer will be 64 bits, zeros or ones. Okay, and as I have mentioned, there is a link in the Q&A. Okay, so I'm going to give you some time for doing this. Good luck. Okay, the time is over. Let me check how many answers. So we only have 14 responses. I don't know if you need more time or where I see more responses arriving. So this is, yeah, most of you have the correct answer. Okay. And let's see why that is the correct answer. So what we are doing here, let's go instruction by instruction. So first of all, this instruction. So what is doing this instruction? We are going to modify the first quadrant. So logical shift left 0. By this, we mean that we are going to modify these 16 bits. What is the value of, what will be the value of those 16 bits? The value indicated here, okay? With this operand, we say which quadrant, which 16 bits are we going to modify. And with this operand here, what we are saying is what value are we putting into the quadrant indicated by this operand. So in this case, we are putting the number 1 in the first quadrant. So here, the number 1 in binary is also 1 in decimal, okay? And then this is what we get. And as we have here a set, everything, the rest will be 0. Okay, so the next instruction, in the next instruction we have a K, and then what we have here is that we want to modify, in this case, the second quadrant, okay, those 16 bits here. So what will happen, that all the bits will remain unchanged except for those 16 bits here, in which we will add a 1 again. So then the red part will be modified, okay? So this 16 here indicates that we are going to modify this quadrant, and this one here indicates the number we are going to add here. Okay, so you can see that this 16 is like actually a logical shift left. So logical shift left 0 is just we are here. Logical shift left 16 is that we do 1, 2, 3, 4, 5, 6, 7, and then 16, and then we start adding the numbers. Again, here 32. This means we are going to modify the third quadrant, and we are going to put an 1 again. And as we have the K, we are going to keep the rest of the bits. So that means that only the red bits changes, okay, the third quadrant. If we again count 1, 2, 3, 4, in the end this will be the position 32, indicated by this value. So at the position 32, we add the value of this operand, which in this case is 1, okay? And then finally, well, not finally, and then we have this other instruction in which we modify this this value. Okay, so I think that there was an error in the form. Okay, so I think that the correct answer, the answer marked as correct, was all zeros. But okay, no, it's okay. There is one still. There is still one instruction. Okay, so this 48 here means that we are modifying this quadrant here. Okay, so if we count here 1, 2, 3, 4, 4, this will be the position 48. Again, we are putting a 1 in this position. As we have the K, we keep the rest of the values. Okay, and now yes, the final instruction here is where we have the trick. So here there is a set, which means that we are going to put zeros, to set to zeros to all the positions except for the first quadrant, in which we are going to add a 1. Okay, so then all the positions will be set to 0 because we are using the set instruction, and in this case, this part in red will be the result of adding the operand here. Okay, it's clear? Let me check if you have any answer. I see a lot of answers here, so someone is asking, how has the first 32 bits changed in the second step in slide 13? Okay, so in the second step, so this is first step, and this is the second step. So, and you are, yes, this is a copy-paste problem. Yeah, you are totally right. So I'm going to modify it. Yeah, you are totally right. Sorry. Yeah, I was just copy and pasting everything. So yes, so to be, yes. So this should be 0. So yeah, there was a mistake there. So now it's correct. Okay. No, not yet. So we have still this one here. Okay. Yeah, so many thanks. So yeah, I'm glad to see that you are attending, and yeah, that was a mistake. Okay, so I think that now is correct. Yeah, okay. So before I have copy and paste the instructions, and we have here a couple of ones, and I have removed them. Okay, the only value which changes with this instruction, so is in this case those bits, and the rest goes to 0. With this instruction, the only value which changes are those ones. With this instruction, only change the red. Okay, the values in red, and in the final instruction, also change the ones in blue. Okay, I think I can add more colors to make this more obvious. So I think that now it looks it looks better. Okay, so it's more clear. So with this set, we are also saying that all these bits goes to 0, and this one means that those instructions are modified. Okay. Okay, let me see. I don't see. I think that all the questions have been addressed right now. So if not, is your time to ask something related to this, because I think this will be the most complicated thing. The rest of the addressing modes have already been seen. Okay, so it seems everything is clear with this. So now I'm going just to name do a summary of the different addressing modes. So apart from these immediate wide operands, we can also modify all the values in a register by using what we call addressing modes. The immediate addressing is what we have already seen. What we already know is the add I instruction. So with this, we can modify up to 12 bits of a register. If we need to modify more bits, we can use, as we have seen, the immediate wide operands, but also we can use the register addressing, in which we are just saying, okay, set one register with the values of this other register, and with this I'm modifying the register completely. We can also use what is called base or base addressing, in which the operand that we want to modify is at a memory location, and for going to that memory location, we calculate the address of that memory location by adding a register and a constant in the instruction. And then we also have the PC relative addressing, which is when the address to which we want to jump is the sum of the current address of the program counter and a constant in the instruction. Okay. Okay. There is a question regarding the formats of here. So someone is asking, when do you know which formats to use? So here, for this, you need to go to the, remember that we have the Legviite reference data, and here you can see the format. So for instance, if we want the mov set and mov kate format, we see that is IM. Okay, so IM, then I know that I need to use the IM format. If I'm using other instructions, so we have here also the format for those instructions. Okay, here we have also the format for those instructions. Okay, but basically we will see here in this reference data the format for each instruction, and that's why we know which format follows each instruction. It has already been defined. Okay. So the test, someone is asking if the test will be multiple choice. No, so we cannot do it multiple choice. We are not allowed because it's done online. And regarding the how many questions and so on, as mentioned, I'm preparing a practice test, so you will see the practice test will be something very similar to what you can expect. So today focus on the lab that we are doing this afternoon, and don't worry that on Friday we will release the solutions of the lab, and hopefully I will also release the practice exam. Okay. Okay. So some last questions. Someone is still asking, when do you know how to use immediate white operands? I guess that the question is when to use immediate white operands, or when to use just the add I instruction. So it depends. So with this white immediate operands, I can modify up to 16 bits in each instruction. And if I do multiple instructions, 4 instructions, I can modify the 64 bits. But however, with the add I can only modify 12 bits. So you see here the add I can only modify 12 bits. So if with only 12 bits it's enough for me, then I can use the add I. If I need to modify more, then I will need to use either the white immediate operands or any of the other addressing modes. Okay, so yeah, I hope it's this part of the module is clear now. So many thanks for listening. Yes, and have a nice rest of the day. I hope you enjoy the lab, and good luck in the test. And if you need something, as I have mentioned, the ticket system is available. The email is also available, and we are always happy to help. Thank you very much, and yeah, have a nice rest of the day, and good luck in the exam. Bye bye. See you.